All right, we're back with chapter 14, frequency response. Not that its other chapters are less important, but this frequency response chapter and this topic has always seemed to me really universal. Things, whether they're mechanical uh, or electrical or populations, they tend to work with frequencies. They tend to move with frequencies. So let's get to it. The basic idea, the thing that's going to carry us, a basic notion is called the transfer function. And the transfer function, we just indicate as a box, and it says we're going to relate the output to the input, something that we can call the output to something we can call the input as a function of frequency. So over here we're just stating that this almost seems too obvious, okay? But you may recall in other courses or earlier in this course where boxes like this, modules, have been put together and you just connect the output of one to the input of another, output of one to the input of another. And maybe there's some connection back from one output to another input. When we can characterize a circuit as a function of frequency, that's what we're going to be talking about here. And so far, it's been a function of time. We've always had cosine omega t as a driving force, but omega has been specified. We've not had a variable omega. Most things in life encounter variable frequencies, and so those are the things of greatest interest. The transfer function of a linear network can be expressing basically four different relationships between output and input. Electrical circuits I'm talking about here. We could simply be talking about voltage gain. What's the voltage out? Oh boy. What's the voltage out as a function of the voltage in? Given that the voltage in, of course, is going to be a function of frequency. All right, so here we've substituted for y and x, we've substituted V out and V in. We can also be talking about current gain, simply the current out divided by the current in, both as a function of frequency then. We could also be relating output voltage to input current, right? Transistors do this. Various types of transistors. We'll do a transfer impedance, okay? And we can have the dual of that to transfer admittance, where we're actually tracking output current as a function of input voltage, a driving voltage, okay? So these things happen, and we can in general say that the transfer function will have a numerator as a function of omega and a denominator as a function of omega. Sounds kind of trivial, I know, at this point, but we'll soon be putting a lot of legs on that beast. The thing to notice here is if I have a function like this that captures a numerator and a denominator, such as this, like crystal clear, both as functions of omega. The transfer function, if I try to plot it, is going to have zeros any place the numerator equals 0, and something we call poles every time the denominator equals 0. So when we're trying to figure out how does the frequency response go, we're going to be looking very carefully and quickly right away at these zeros and poles, because a numerator function that goes to 0 makes the magnitude go to 0, and a denominator function that goes to 0 makes the magnitude go to infinity. Not sure what whoa, going the wrong way with my charts here. Okay, so again, just a simple statement. This is in your book that the 0 pushes things towards zero, and a pole pushes them to infinity. And it's the combination of multiple poles driving the denominator maybe up, and then there's a counteracting zero or something. This is what we're going to explore. There's also, by the way, a substitution, since we're basically going to be dealing with polynomials here, and they're going to be complex. Hence, they're going to be filled with a lot of j omegas. At some point, even in one of the examples here, we're going to start substituting s for j omega. Makes the math a little easier, and makes our talking points a little easier. And you can always back up by taking powers of s and substituting in j omega. Nothing got lost there. It's just a little easier to work through that way. And I'm going to get right into this with practice problems. There are plenty of examples throughout this whole chapter. It's very important to take your time working through as many or all of them that you can. I was thrilled to see the chapter is quite full of examples as opposed to just laying down a lot of theory. So here we go with this one. We've got a simple driving function here. Where am I? We got a driving function here. Whoa, here it is. That's just Vs, right? And we can just say as a starting point that it's some magnitude at an angle of 0 degrees. And we've been doing this all along, right? Now, if I look at this circuit over here, it's really just a voltage divider, right? I can look at this guy as saying the admittance is j omega L, or the impedance is j omega L. And so I could very easily say right away that any transfer function V out over Vs is simply going to be what? The amount of voltage that falls across the inductor against the total amount that falls across both the inductor and the resistor, right? So that amount as a simple voltage divider is just j omega L over R plus j omega L. All right? And the fun can begin when the factoring starts here, but this is what we get right away out of this circuit. Okay. Now we can, without going further, we can do some analysis from here and come up with a picture of what will the frequency look like when and what will the phase look like as I mean, not frequency. What will the magnitude and phase look like as omega increases? Okay, so let's take a minute here. I'm going to. This is certainly a very acceptable way to present the result. All right, but I'm going to take it a step further to make it a little easier for us to plot the magnitudes and phase angles. I'm going to make the observation that when omega is equal to, what do we have? Well, let's do a little factoring first here. Let's divide the top and bottom by j omega L. So this will give us 1 over 1, that's this part, minus j times 1 over omega R over L, right? I just put the minus sign j to move it up into the numerator of that bottom here, okay? And so you'll notice if we hit a frequency, omega, which we're going to call omega 0, and there are always these omega zeros, sometimes many of them, but it's going to be the frequency that makes this whole term be what? 1 minus j1. All right? And that frequency is what? When omega is the inverse of this portion, right? So when omega is L over R, we call that omega 0, then our transfer function becomes 1 over 1 minus J1. Okay? I did that backwards. This should be when omega is R over L, right? Because if I plug that in here, I'll get R over L. The L's will cancel, the R's will cancel, and end up with 1. Sorry, my bad. So but that's an important frequency, and it's one thing that we'll call a break frequency. You'll notice a couple of things happen here. If I solve the equation with this in, then I've got the transfer function at omega 0 is 1 over 1 minus J1. But that means the magnitude, right? The magnitude is what? 1 over square root of 2. And the angle, this much produces what? Minus 45 degrees. So the phase in the numerator will be plus 45 degrees, okay? We're going to see these kinds of relationships all the time, and these turn out to be well-recognized numbers. And later we'll be talking about decibels, and we'll learn about 3 dB points and all this sort of thing. So let's just take a quick sketch here of take a try from what we've learned at frequency, and I may be writing over what I'm going to do, but let's do it anyway. Here's omega, and this will be the magnitude on this side. And so we've already identified one point here. That's at omega 0, where we've got what? 1 over, well, we've got 0.707, right? 1 over the square root of 2. If we let the frequency go on out to a huge number, right, infinity, then omega gets really large. This whole term here, right, for omega approaching infinity, this term, the term approaches 0. So h will approach what? 1 over 1. So that's going to be our max value up here. So we know there's a point there, there's a point there, and there's a smooth point out here. So we know there's going to be something, curving out there as omega increases. We'll get more familiar with believing that, but that's where that function is going. Phase angle, right, as a function of frequency, we've got these same interesting points, right? Here's our omega 0, and we know that that's 45 degrees. It's plus 45. So there that is. Let's do the same thing. As the frequency gets very large, the term omega, the J term, disappears, so we get 1 over 1. And the phase angle of that is 0. So out here we're heading toward 0. We pass that point. If the frequency is 0, if we're way down here, the frequency is 0. 1 over 0 is infinity. So the tangent of a minus big number against 1 is going to be 90 degrees, right? So we're going to start at 90 degrees and curve our way down through here. I'm not drawing this very well, but it's going to go like that, okay? And you just work that stuff out. Here are the two pictures in beautiful, smooth, colored form and that, but we got the idea. All right, let's try one more problem before we leave this section. Here's the same idea. Now, we could attack this in a lot of different ways. This is a current divider, like the last one was a voltage divider. And we can go after this in a number of different ways. Easiest might be to say, well, V0, right? V0, occurs across both of these, right? And what are we going to be going for? The output voltage as a function of the input current. We need to identify where is that output voltage. Oh, that's back here. We're actually looking at this guy, right? So really all we're solving for is it's VO. I called it output, but that's a misnomer. So we need to find this current as a function of that voltage. But look, that voltage passes right across these two. So we could remake this as our source, an impedance here, and another impedance here, right? And we can easily say with omega, this Z is 10 plus J omega 2, all right? And this Z, so we'll call this the right-hand one, and we'll do a left-hand one, and that will be 10, plus, what is it, 1 over J omega C. So it'll be 1 over J omega, and C is 50 millifarads, so that's 0.05. So that one might need a little cleaning up as 10, and we can keep this as plus or minus or whatever we choose. But the 0.05 up top will be, we can leave this as, well, let's just do this, plus 20 over J omega. Okay? And now the transfer function is, if we're looking for the I, is really, this is one of those impedance transfer functions, right? Where Z total, how could we write this? Z total is equal to V0 over I0, right? That's just Ohm's law, or IN. That's just Ohm's law, right? So what we want to find, this is expressing what is the parallel combination of Z right in parallel with Z left, okay? So I'm going to introduce in a user form here the S term. And so I'm going to substitute S equals J omega. And so Z left will be 10 plus S2, or 2S I should say. I'll clean that up the next time. And Z right is equal to, what will this be? 10 plus 20 over S. Okay, so now let's just find the parallel combination. And what is the parallel combination? It's, I claim that the transfer function here of omega, or actually we'll make it of S for the moment, will be Z left times Z right over Z left plus Z right. Yeah? Okay, so let's just do this. Let's see, the left is 10 plus S2, so we got 10 plus 2S, I'll call it, times 10 plus 20 over S, all over the sum of those two, plus 10 plus 20 over S. Okay, so why don't we do this? Let's clean up the S's at first. So in other words, I'm going to multiply the top and bottom by S, right? I'll multiply this by S over S times S, and all of this times s. Right? So this is going to give me, the s is going to clear this, right? So how will I write this? I just want to be careful how I write this. It'll be 10 plus 2s. A lot of ways you could probably go after this. And then you could have 10s plus 20, right, over. Do it again here, and we've got 10s plus 2s squared plus 10s plus 20. All right, let's just keep going and multiply all this out. So on the top, we've got 100s. We could have done all this before we multiplied by s, but so 100s plus 200. That's the original 10 times both terms on the right-hand side. Then 2s times 10s will be plus 20s squared, and 2 times 20 is plus 40s. Okay, and this is going to be divided by, it looks like 2s squared plus 20s, right, plus 20. Okay, it's starting to shape up a little bit. So if we combine terms on the top and divide by 2, right, I'm going to do that right here. So I have, let me do the bottom first. So I show that division by 2. That'll be s squared plus 10s plus 10, right? And then on the top, I'm going to pull the terms together. So everything is individual except this 100 plus 40. So 140s, and I'm going to divide it by 2, so that's 70s. And in fact, I think I'll pull out a 10 as well. So 10 times, you see where I'm headed, 10 times, I've got 7s. So I'm just going to anticipate what's going to happen here. 7s. Then I'll take my s squared. I divided by 2 and I pulled out 10, so this will be s squared. And then the remaining term, I pulled out 2, making it 100 and a 10, right? So this will be a 10 over here. Okay, and we know, we can see this coming. This is kind of the direction you're always going. You're going to try to be factoring things or setting up prime factors or factors of any sort, prime or not, right? So I'm just doing the upper, and the bottom will be, what are we going to have there? I guess we'll just have to leave it. We're going to have to actually use the quadratic equation here, right? But you see where I'm headed. I'm creating a numerator where it's easy to determine what's going to cause a 0 here, right? And on the denominator, I'm going to want something of this form, right? S, both are plus signs, so we'll try for pluses, and S, blah, blah, blah. So we're going to have to solve for the roots of this, the roots of the denominator, the roots of d of s, right? And so that's going to be our good old roots of the quadratic. So that'll be minus b, s will be equal to minus b, so that's minus 10, plus and minus the square root of b squared, so that's 100 minus 4 times a, 4 times 1 is 4, c is 10 minus 40, right? All over what? 2a, so 2 times 1 is 2. All right, so this thing becomes obviously 60, so it's minus 10 plus and minus the square root of 60 over 2. All right, now we know from inspection that the square root of 60 is going to be less than 8. Not a lot, but somewhat less. So we're going to have minus 10 plus and minus something a little less than 8. So I'm just going to fill in some roots here, and I'm going to say, let's say the square root of 60 is what? If 7 squared is 49, 8 squared is 6. I'm going to call it maybe what? 7 and 3/4. Yeah, that'll do. 775. Let's just call it that. So that means S is going to be minus 17.75. Oh, and another root will be minus 10 plus this. Looks like it will be minus 10 plus this will be about minus 1.25. Yeah. Oh, no, 2.25. Is that right? Yeah, 2.25. All right. And then those get divided by 2. Right? Divided by 2. Don't forget that. All right. So this is going to give us something just under 9. So I'm going to call this minus 8.8. And the other root is going to be minus 1 1/8. It looks like 125. Okay. So those will be the two roots. And the denominator then can be written as the denominator of S can be written as, what have we got? S. If the root is going to be minus, it's going to be S plus 8.8 times, let's be careful here, S and 1.125. So let's check this out before we assign signs. We're going to want this 8.8s plus 1.25s to be plus 10s. And then we want 8.8 times this. Yeah, these are both going to be plus. And I may be a little big in my estimate. So you can see I'm going to have poles at minus 8.8 and another one at minus 1.125. So that those two frequencies, or j omegas, are going to want to drive it to infinity, and the zeros up here of 5 and 2 are going to want to turn the thing into 0. So as those two items, poles and zeros, play off against each other, we will get a frequency response that tends to go, possibly modulates up and down a little bit. I don't know. All right, we'll be next. We're going to move on to something called Bode plots. I'm going to say quickly, by the way, even though it's a skippable section, I can say a few words quickly about the decibel scale that will maybe eliminate confusion later, because decibels are thrown around all the time in the commercial work and in hi-fi work, all sorts of stuff, any signal processing work. So let's just remember 4 simple rules about logarithms and the arithmetic of them. If I have, as in this case, the product of 2 items and I take the log of it, it's the sum of the individual logs. Likewise, if I take the quotient, it's the log of the numerator minus the log of the denominator. And if I have a power of some function, the log of the power is the power times the log of the basic function itself. And then the all-important one, many times, the log of 1 is always 0, no matter what the base is. Okay? And this log is referring, by the way, to a base 10 scale, although it's not said here. When it's written as log as opposed to ln, and there's no specified subscript down here like a base 2 or some other base, it is assumed to be 10. Okay? Now, so G is the number of bells. We're just calling it that. And the bell is a pretty large term, but here it is in full regalia with the base specified. So the log of the ratio of the powers is called the number of bells. Now that tends to be kind of a small number at times. So we've really redefined it to define the decibel as 10 times the bell function, okay? And it just makes it a number that's not always fractions and so forth. The decibel, there's a couple of important decibel numbers. The decibel of the number 2, if you do the math, is about 3 decibels. And so you often hear talked about the 3 dB point. And what that means is it's what? The power doubles, or whatever the transfer function is, the value doubles. Going the other way, if it goes in half, it's the minus 3 dB point. Because in logs, the log of the fraction is just 1 over that, right, from the power here, item number 2. So you have the plus and minus 3 dB points. When does the transfer function value, magnitude, go in half, or when does it double? Okay, those are important points. If I look now at just a basic network, this is our 4-terminal network, but all the voltages, voltage 1, 2, current 1 and 2, are identified, but a transfer function is going to relate 2 of them, any 2 of them, right? So if we're relating power, to power over here in this is our decibel function. But if we write that in terms of voltages, we end up with voltage squared divided by resistances, okay? And if we take that another step, we end up with voltage squared, voltage 2 over voltage 1 squared, right? Because all we're going to do is just do the math of these 4 things up here. We're going to apply it to this little deal. And it's going to break up into the sum of 2 quotients, right? And so here's the one of interest, the voltage relationships. And this is a tag along, the decibels of the resistances, right? And if this resistance ratio, is equal to 1, in other words, the input-output resistances are the same, then this whole log term goes to 0, according to number 4 up there, okay? And when we do that, then we're left with, and I've taken it apart here, but we're left with, on the left side, we take the power off, and instead of 10 log, it becomes 20 log of the voltage ratio, right? So what happened here is the power ratio and decibels is 10 times the log of that ratio. The voltage transfer function gain in decibels is 20 times the ratio of the voltages. Okay? So that's just, these are now become definitions, and the same is true with currents. Okay? So you'll see this going back and forth. When things are talked about in terms of voltage or current, you gotta think of it as 20 times the log of the ratio. And if you're talking power, you're saying it's 10 times the log of the ratio. Okay, so this is our basic intro. And the next section is one we're going to spend a little bit of time on, the one on Bode plots. So that will be part 2 of chapter 14.